slideshow? Trish?
We can see it, Matt.
Yes.
Oh, okay, perfect. Great, all right. So hi everyone, my name is Matt Davenport. I'm a graduate student at the University of Texas in Austin. With me here is JC, also a grad student at UT. We're in the same research group and we both work within CISTAR. Also joining me, I'm really happy to introduce you to Elizabeth Bickel, who is a graduate student at Purdue University in Indiana, and also Elsa Koninckx, who is a graduate student at Northwestern University in Chicago. So we're here to talk a little bit about CISTAR's mission, give you an overview of some of the research we do to contribute to that mission, but also most importantly, just introduce ourselves as people who have, not.
Matt, you accidentally got muted. You have to unmute yourself. There.
Okay, how much of that was I muted for?
With like 2 seconds.
Okay, all right, I'm not sure how that happened. Thanks for letting me know. And if anything like that happens in the presentation, please, anybody just holler. So we are here to introduce CISTAR and the research that we are doing as part of that mission, but also to maybe give you some example of people who are in STEM and our backgrounds and our pathways and how we've gotten to where we are, and we wanted to provide a space where you can ask us questions and we can just have a discussion. And this is certainly fairly informal, so if you have any kind of questions, please feel free to ask them at any time. So let's get started. Elsa's going to start us off.
Yeah, so first we just wanted to start off by maybe thinking about what sort of products out there in the world are actually coming from petroleum, or crude oil, we can also call them. So maybe just give a thumbs up if you think, say, light bulbs might have come from crude oil. Hopefully not.
I'm not sure if they have thumbs up in Google Meet.
That's fine. I'm watching everyone. Don't worry. Or maybe things like motor oil is another thing, in which case, yeah, I did see a few signs. Yeah, I think crude oil, motor oil, it makes sense. And then things like soda cans, no, not so much. But if we go to the next slide, there are also a few more examples, and I think a few examples you'll find very surprising as well. And so, for example, things like golf balls, you might not think are coming from crude oil, but a lot of hard materials are actually side products of oils and plastics that are coming from the same source, gasoline. Things like crayons, these waxes, and if you looked at it chemically, these are very long chains of molecules, and so very similar to plastics, crayons are coming from crude oil. Similarly, things like guitar strings can be, again, these very long chains, and can actually come from crude oil as well, from things like nylon. If you've heard, your clothes might have nylon as well. Including things like this fishing tackle, rubber boots, very similar to sort of wax crayons. They both have this slippery elasticity to them. And even things like chewing gum actually have products that are coming from crude oil as well. I think the next slide has even more examples if you're curious. Again, things like yarn, nylon, all of these very complicated materials are all coming from this single source. And things like kayaks and even contact lenses, which people put in their eye, well, guess what? It's another crude oil material. And so on slide 4, because of all these things coming from crude oil, do you think we can keep using crude oil forever? Or do you think we could find a replacement for when this inevitably runs out? Because crude oil is not renewable. There are only a certain amount of it in the ground, and what are we going to do when that happens? So ideally, as scientists, we want to build a future that uses renewable energy, but we're not actually ready yet. So solar panels and wind turbines, they're really starting to kick off, but they really haven't made it to the point where the whole world can use it and the whole world can be powered by just these. And so the United States has a lot of this shale gas, which hasn't really been being used as much as things like gasoline that you put in your car. And so this shale gas is really what we as a research center are focused on in order for us to transition to using renewables. And I think we're going back to Matt now.
Sure. So really quickly, I just want to introduce myself a little bit more in detail because I'm actually a native New Mexican, even though now I live in Texas. So, and I actually work at Los Alamos National Laboratory as an intern at one point. So if you have any questions about that, I can try to answer them. I'm a graduate of New Mexico Tech down in Socorro. That's my graduating class in 2018, chemical engineering. And like I said, now I work at the University of Texas. There's a picture of my research group and me making membranes. So please feel free to ask me about any parts of that. I just thought I'd point that out, that I am a New Mexican and maybe have a perspective that could be beneficial to you. Okay, so continuing on, what is shale gas, right? So shale gas is primarily composed of smaller chain alkanes, right? Or so things like methane, 1 carbon, 2 carbons, ethane, and propane. The vast majority is methane, right, which has only 1 carbon. But as Elsa was kept pointing out, you know, we need these waxy, longer chain products in order to make consumer products, as she was discussing. But for your car, you need octane, or what we call, you know, gasoline, but you need octane. You might recall when you're at the pump, the fuel has different octane ratings. So we essentially need to go from these short molecules to longer molecules if we're going to transform shale gas. But what's the problem? So it's extremely expensive to churn short molecules into longer molecules. And the other thing is that these chemicals are gases at standard conditions. So they're very expensive to transport. So oftentimes companies will forego dealing with that and attempting to turn that into a product, and they will simply burn it into the atmosphere. It's called flaring, and you can see a picture there. Here's a very dramatic demonstration of the scale of this activity. This is a picture of Texas at night. You can see San Antonio, Austin, Houston. So south of San Antonio, there's this swath of lights that you can see by satellite at night. And that's actually activity in the Eagle Ford Shale region. And so that's all flaring that's occurring. So there's an extremely large amount of wasted resources occurring every year. And so we in CISTAR would like to reduce the amount of waste that we are creating. And part of that is through catalysis, and another part is through separations. So as I was alluding to, there's been a huge shale gas boom. I highlighted here you can see the price of natural gas on the y-axis on the left. So it's been going down steadily. And shale gas production in the United States over the last 10 years has simply exploded. And you can see I've broken it out by regions here. And New Mexico actually, as I'm sure you're aware, has a large amount of shale activity in the southeastern portion of the state. So there's a boom right now, but these oil companies don't have a lot of incentive sometimes to pay the cost for transporting the shale. And so sometimes it's flared. So 1,400% increase in domestic production and a huge billions of cubic feet of natural gas is flared globally. That's where CISTAR comes in. I don't know how that got shifted, but so CISTAR stands for the Center for Innovative and Strategic Transformation of Alkane Resources. And we are divided into 5 research thrusts. So everybody is working on a little piece of the problem. Problems like this are so large and so complicated that one person or research group is simply not able to bring the necessary expertise or mastery of all the concepts to solve it. And that's true in industry as well. You know, companies have divisions that work on different things. So even though we're academics working in universities, we all work together as a team, solving our own little piece of the problem. I won't go into all the details, but thrusts 1 through 3 are related to catalysis. We also have process modeling. The process modeling people let us know what sorts of performance we need out of our research in order to get, in order to be profitable. They give us overall analysis, economic analysis, and then there's also separations because we need to separate the products from these catalyzed chemical reactions. And the idea overall is that we will be able to together develop a mobile modular gas plant, which is something that does not exist right now. So a gas plant that can fit on a semi-truck so that we can drive it out to these more remote areas where oil and gas production is occurring and process the natural gas into liquid fuels at the wellheads and prevent it from being wasted and flared. So that's our goal, and now we're just going to talk a little bit about how our research fits into that. Take it away, Elizabeth.
Hi everyone, my name is Elizabeth, and I'm a graduate student at Purdue University. I actually grew up in Tennessee and did my undergraduate work there in chemical engineering, and there are some just fun hobbies and facts and things that I enjoy when I'm not doing science. But I think I have a really cool job. I get to study some of these materials that help us take the small molecules Matt was telling you about in the shale gas and grow them into the big long molecules you see at the bottom of the screen. And so if you were to just mix these really small molecules together and set them out, nothing would happen. It would take a really long time for that reaction to happen. So instead we use these materials called catalysts, and those make the reaction go faster. And you can see the blue structure that I have there is the type of catalyst I work with every day. It's called a zeolite. And there are over 2 million different types of these catalysts, and we don't want to sit there and test them one by one. So instead, as engineers, we need to think about and figure out what properties of those catalysts can make our reaction happen faster and still give us the long molecules that we want. So I think my job is really exciting because for me, I do experimental research. So I work in the lab every day. And for me, the periodic table of elements is kind of like my set of Legos. I get to take these atoms, I get to stick them together and build a catalyst structure. And just like with Legos, there are some atoms that work together better and can make better and structures of catalysts that we can use. So we can combine these different atoms and build catalysts for the reaction and see how they work. So one part of my job is doing synthesis. I make the catalysts from raw materials. So in a typical synthesis, to make these catalysts, we're looking at the 2 elements I have circled in red, aluminum and silicon, and that's what makes those zeolite catalysts. And we can do a synthesis by mixing something called silica, which is actually pretty much very similar to sand. We mix it with water and salt, and we heat it up and stir it, and we can actually make those zeolite catalysts. So if I have a really high-powered microscope that lets me see really small things, I can actually zoom in and look at these crystals. So if you think about how thick your hair is, each human hair is about 100 microns. And the pores, the little holes on the zeolite catalyst, are 10,000 times smaller than the width of your human hair. But we can see them with this electron microscope. And that's what you see these pictures of here. These are some different types. And you can see the structures look different. So we want to look at how these different zeolites can take propene and the small molecule and grow it into this larger molecule. So I was wondering I don't know if people can use the chat or not, but I want you to think in your head as we go through this presentation, what properties or what things might be important to think about as an engineer designing a catalyst. Maybe we can talk about that more in the Q&A. And this last thing is a video. So if you're a chemical engineer, you get to work on all length scales. So this is a chemical plant at the kilometer scale. Now we're going to zoom in to a chemical reactor. So we're getting closer and closer to the plant. You can see all of these different things within the plant. But now we're going to zoom in on a reactor, which has brown and yellow cubes of catalyst. And so these catalysts are really big chunks of those crystals that I showed you. And if you keep zooming in to a really small layer to see single atoms, you can see these atoms, they land on the catalyst surface, and you can see the catalyst helps those bonds between those atoms break apart, and you can form a new atom on the catalyst surface. So that's what the catalysts that give you your products that Elsa was talking about, snowshoes and chewing gum, that's what they do on the atom scale.
Thanks, Elizabeth.
Okay, so hi, I'm Elsa. I'm doing these chemical reactions, but I'm actually doing all of these on a computer. So all of these really cool details Elizabeth just talked about, she's doing them, physically adding materials together, but I'm actually doing this all based on a computer. So I'll go through a lot of coding, and I'll have to do a lot of logic in order to understand, if we have this small molecule and we're going to make a large one, well, there's a lot of different pathways to get there, where I could combine just immediately 8 of them and get to my C16, or maybe I'll go piece by piece. And so we're not really sure what's going on. And so I will help Elizabeth with her data, and I'll just sort of be able to take an even closer look at it and try to explain this. And as Elizabeth said, we can do this at multiple scales. So there are a few modelers who are looking at just individual molecules. So at the very end of that video, when we zoomed in super duper far and we're just looking at single atoms, we have a lot of computer programs and mathematics that will look into how much energy it takes for this to happen. And from this, we can predict which pathways and which options our molecules have to take. And likewise, we can go very large, and we can look at overall reactors and overall plants. And from that, we can design sort of reaction models, which is more my size scale. And so we can simulate, without having to do these experiments now, exactly what would happen. And so I also love my research. It's really interesting and fun. And if you find yourself growing bored at one scale, you can always go to a different scale.
And Elsa, didn't you just come back from a study abroad sort of experience?
Yep, I did actually. So I was in Belgium, which is a very small country, sort of sandwiched between Germany and France. And so there I also was working on learning sort of how they're doing simulations versus how in our group at Chicago we're doing simulations. So it was an extremely fun experience. You can definitely go see the world while you learn about molecules too.
Absolutely. All right. So as I already introduced myself, my name is Matt. JC and I work in kind of a similar area, and I'm kind of on a different side of CISTAR than Elsa and Elizabeth, though again, we are still working together towards the same goal. So we study separations. Once you've performed your chemical reaction in the reactor as Elsa studies, or you're studying those single atoms and how they react in experiments as Elizabeth's doing, to actually use these products industrially, you have to separate out the product you're looking for from everything else. If you cook pasta in water, you have to get rid of the water, right? So that's a very easy separation to do, because you can do it with a colander with giant holes. It's a lot more difficult to do that when the things you're trying to separate are small molecule hydrocarbons that are basically the same size from the perspective of your sieve. So we work on polymer membranes. I have a picture of a polymer here. It's essentially a really long chain molecule. And as I've shown here, the circle represents a gas molecule, such as an ethane or a propane or a propene, as they were talking about earlier. And these polymer chains wiggle. They have residual thermal energy. Anything that's not at absolute zero has some thermal energy, and they're wiggling. And so over time, spaces form, and these gas molecules are able to hop between what we call free volume elements, between these spaces. And over time, through the solution diffusion process, which I won't get into, but you are able to perform a separation and concentrate one of the species. So here, the smaller tan circles are being concentrated, whereas these larger red ones are being excluded, you could say. And this has a lot of practical benefits. One is that because membranes rely on surface area rather than a volumetric process, you can pack a lot of surface area of membranes into a small space by wrapping them up in clever ways. And so you're able to replace very large pieces of equipment, such as this amine scrubber. Amine scrubbers are used to remove CO2 from flue gas, which is the output from like a coal-fired power plant. And you can, instead of using an amine scrubber that's this gigantic column, you can use a smaller membrane unit, which is modular. And remember, we're trying to develop a process that can fit on a semi-truck. So this is really essential for how we're going to be doing these separations. And my specific research project is separating ethylene and propylene from ethane and ethylene, or from ethane and propane. It's a huge business, 200 million tons produced a year, and right now it's done in a gigantic column like this at minus 160 Celsius. So it's cryogenic distillation, extremely energy intensive. And if we're able to succeed in creating a membrane process for this, it will lead to an unbelievable amount of energy savings, and which is very beneficial for our planet. Daisy?
All right. So hi everyone, my name is JC Davila. Like Matt mentioned before, I also work in the separation side of CISTAR. And just to introduce myself a little bit, I'm originally from central Mexico. So I'm from a city called Santiago de Querétaro, which means the city of pine cones, although none of them are left at this point. So the picture at the bottom right with the aqueduct, that's kind of like the downtown area of the city, but it's relatively small. And so I grew up there, and I did like half of my high school there, or up to half of my high school. And then I finished up and graduated from Round Rock High School here in Texas. And then I went to Texas A&M University for my undergraduate, and now I'm working in the separations labs here at UT Austin. But I actually also have visited New Mexico several times, and one of my favorite places is the Pueblo Pintado. I think it's somewhere northwest of Albuquerque. So that's a picture there. And then we also, CISTAR team on normal times, right, like before the pandemic, we would actually all meet in one of the different schools and sort of explore, like one time we went on a field trip to one of these gas fields to learn about how this gas processing plants work. So the bottom left picture is of me on the gas field. It's actually really small. There's only like a little pipe sticking out of the ground. Everything else is buried. So there's not that much to see, but the scenery was still beautiful, and getting to learn about the process is always interesting. So specifically what I work in, I also make membranes to try to do some of these separations. So again, I have like this long polymer chain that has like a lot of free volume. You can think of it like when they're all tangled up, they're kind of like a sponge. They have all of these empty holes or empty space. And so normally gas molecules can get in there and hop from those spaces and essentially permeate across a membrane that we make out of this polymer. But so if these voids are like really large and there's not any like particular interactions between the polymer and the gas molecules you're trying to separate, your separation is not going to be very good. So what I'm trying to do is improve how much of the element that you want to separate actually permeates across the membrane by adding a liquid salt that really likes the component we're interested in. So the example I was going to give you guys is we have the smallest hydrocarbon, like one carbon, it's methane. And usually it's going to be mixed up, right? Like the gas that people flare, it's usually the majority methane, like 70, 80% methane. And then the rest will be like slightly bigger. So C2 or C3, right? So in this case, I'm showing C3, which is the propane. And so propane is a little bit bigger. So actually you can separate the two gases in two ways, right? You can sieve them like Matt was talking about the pasta with the water, and let the smallest molecules permeate through faster and keep out the big molecules on the other side. But there's actually another way that's what I'm trying to achieve, is to separate the big molecules, or have the big molecules permeate faster than the smaller ones. And so that's less understood than the other way, but it's certainly possible. It's been observed. So I also put just like a picture of one of my membranes under the microscope. They're really thin, and we want to make sure that the liquid salt is all across the the cross section of the sample. So that's what I was trying to find out with the microscope there. And eventually, if we get this propane out, we can either use it as is, right? Like if you think of LP gas, it's just like the gas you use to grill outside or that you would use in your house if you have a gas stove. But we can also put it through this process, right? Like dehydrogenate it or essentially get a double bond in between two of those carbons. And then Elsa can use her catalyst, or like Elsa can use her catalyst to grow the chain and make it into a liquid fuel that you can use in your car or something else. So there's many more useful things that we can do with this larger chain hydrocarbons than just the method.
Okay, and you have to get the audio.
That's right.
So we're almost done with our presentation. Before we get to the demos, we're going to show a quick video about research experiences that undergraduates have had with CISTAR. In addition to undergraduates, we've also had high school students. We've even worked with teachers, where we get teachers to come in for the summer and do practical hands-on lab science, and we help them develop a module they can take back to their classrooms and show their students. So we're really big on summer experiences, and this is kind of an overview of what we've had in the past.
Like the best experiences I've ever had. In 2019 by the National Science Foundation. Engineering Research Center, CISTAR, has partnered with NSBE, the National Society of Black Engineers, and their kids camp, known as SEE, to create a summer program like no other. And the fact that NSBE is getting included, it really just made me feel like CISTAR values diversity. The big idea was for undergraduates and teachers to have a chance to do summer research for 6 weeks and then still have time to do a full 4-week cycle of actually spending time inspiring children. The NSBE students, they look like me, they came from my background, so it was a good feeling just to be able to give back to my community. In the program's first 6 weeks, primarily underrepresented teachers and undergrads participate in professional development and research at CISTAR. We have an enormous source of energy in this country that we could use as a bridge fuel until we are able to use renewable energy. We are trying to solve a very difficult problem, and that's where we need people from different backgrounds that have different ideas, different approaches. CISTAR gave me a sense of understanding and a sense that my opinion actually mattered and my intelligence mattered. Working with Dr. Gounder and my mentor Sapiro was a really enlightening, great experience for me because I learned so much. And so now I'm definitely considering going to grad school. Dr. Harris was one of the best mentors I could have ever been paired with him. And I just made a good personal connection right off the bat. In the final 4 weeks, undergrads and teachers serve as mentors in NSBE's SEEK program. SEEK is a free, engaging 3-week program that enables 3rd through 5th graders to not only gain interest in engineering from a young age, but also builds their math and science proficiency to help them succeed in school. You're giving kids an opportunity to understand, hey, I can do that. And I just think that if STEM is introduced to more children at this young age, they could literally change the world. I'm very thankful that this type of partnership exists. It creates that path between being a child to then being a professional and associate of the National Society of Black Engineers. You all are creating a pipeline that gets more demographics into this field. If you touch enough teachers, every student will be touched. My hope is that other engineering research centers and other universities, that they will be able to learn from this and see it's possible to offer this combined research experience and opportunity to interact with kids during the summer. CISTAR program with NSBE, I believe that would definitely increase diversity. I don't think you would have any other choice but to increase it. It's not a matter of, how, it would be just when.
Oh my gosh, Matt, that's a really cool video.
Yeah, right.
It comes every time.
Great. We also, so this is the end of our presentation. We just want to make sure that we extend a thank you to the National Science Foundation for funding us, and as well as our industry partners who have partnered with the National Science Foundation. We have a few demos we'd like to show you related to polymer science. We think they're very interesting and quite dramatic. But before we go to that, I just wanted to open the floor and see if anybody had any questions. I know that there was a lot to take in. Please don't feel any hesitation to just speak up. You know, there's no bad questions, right?
And feel free to ask questions to Elsa or Elizabeth
Yes.
in particular as well. They're also working really hard on their particular areas. So if you're more interested in the reaction side, they can probably answer a little bit better than we can. And we can answer more about the separation side or just the college experience in general. I've gone through that recently, so feel free to ask about that.
Okay, since we have a smaller group, we had a whole class had to leave for their next period. If you guys want, you can just go ahead and unmute yourself to ask questions. If you're not comfortable doing that, you can go ahead and put them in the chat. And Matt, do you want to stop presenting?
Yes, sorry about that.
It's okay. I know I'll start off. I have one thing. I do want information about that SEEK program. I wrote it down, but if you could shoot me an email.
Sure. Yeah, I think, Maeve and Abby and a few other people on the call probably have more info, and I can get that for you as well.
Thank you. All right, guys, don't be shy. Do we have any questions for all of these young people? Well, they're young to me. They're not young to you. Sorry.
Everything's relative.
Right.
Has anything changed with your guys' research with COVID?
Great question. Who wants to answer it?
I can start. For me personally, when COVID hit, we weren't able to come to the lab for obvious reasons. And I think for maybe like 2 or 3 months on average, nobody was able to come and do experimental work. So if you were more on a computational side project like Elsa, maybe you weren't as unlucky and you could still get a lot of your work done. But for me personally, I had to find sort of a new way of doing things, right? So I had to try to get a lot more reading done, a lot more writing done, and simulation, like just at least getting starting to think about simulations, because we didn't know how long we wouldn't be able to come to the lab. But luckily, after the third month, we were allowed back with the precautions in place so that we can social distance.
Yeah.
Wear masks and all of that.
Yeah, as you can see, we have to wear masks when we're inside the building and when we're working in the lab space. We have regulations on how many people can be in the lab at once. So we don't see half of our lab group anymore, hardly. They work in the afternoons and we work in the mornings. Yeah, a lot of things have changed, but fundamentally we're still doing science in here. So it does feel familiar, even with everything going on.
So what is the funnest type of polymer that you've gotten to work with or membrane that you've created?
Funnest type of polymer. Ooh. Well, JC's materials are super cool. I mean, the reverse selective, it process is not intuitive at all. So.
Right. So for me, I think the funnest one that I've worked with was like, there was this polymer. It's essentially the same like silicone rubber that you use to like seal the windows in your house or something like that. But we just turned that into a membrane, and I was also putting like ionic liquid in there. And I didn't know what was going to happen, and it ended up looking like a big cheese, right? Like full of these bubbles. And so the bubbles were like transparent, and the rest of the membrane was like burnt orange, like our school's color. So it was really cool. It was, I think, the first or second membrane I ever tried to make. And it didn't separate anything, but it looked really pretty. And I just didn't predict that would happen. So that was really fun to see.
Yeah, the properties of polymers can change dramatically based on the chemical structure, and then also the way that you process them from solution, or however you're turning them into a membrane. You can create all sorts of structures, and there's a lot to work on. It's a huge field of research, and it's always more to study.
Yep. Great question.
Yeah, great questions.
We actually have a lot of polymers we're going to play with
right
now.
Yeah, actually, specifically some really cool polymers we have set up to show. So that's actually a great segue. I guess we'll start setting up our demos. If anyone has any other questions, feel free to jump in at any time.
All right, so I think we're going to start with the one in the middle, and Matt, feel free to move the camera. So this demo is meant to demonstrate sort of what happens when like a gas producer or an oil producer is using hydraulic fracturing to really get into the gas place and like extract as much resources as they can from underground. So it's really tricky to do because essentially they have to pressurize water at really high pressures, but they need this water to carry with it sand particles. So the sand helps to the fractures that they generate, the high pressure will not stay open, right? There's really high pressure on this rock, so they will seal back up unless you have something to hold them open. So the goal is to get the sand to go into these cracks so they stay open, so afterwards they can get the gas and oil resources out. The way they do that is they use polymers, among other things, to change the properties of the water that they pump in under pressure there. They essentially want it to be viscous enough that this water can carry the sand, right? Like make a suspension, not the sand just sink. If you have pure water and you add sand to it, right? You come to the beach, the sand just sinks. So they need the sand to sort of be mixed up in this suspension so that it will get into all these cracks before they let it rest. And so the way they do that is they start with, we'll just put a little bit of water in this flask. So I'm just gonna start, this is just H2O. And the water they use for hydraulic fracturing is, even after they add all of these polymers, it's still more than 99% pure water. So I'm just going to add a very small amount of this gelling agent, which is just a long chain polymer. You may also know it as guar gum. A lot of food products have guar gum in them to make them a little bit thicker. So it's completely edible and not a harmful polymer. You're just going to add maybe about a teaspoon or so. And you can see that it dissolves readily. Perfect. Yeah. I realized you moved the camera. Great job, Matt. So as we mix it up, it readily dissolves. And you can see that the liquid turned a little bit thicker. But it still sort of flows almost like water. Like this is still not going to hold sand very well. So what we really want is we want to, now that this polymer is dissolved in it, they're all long chains of a polymer, but they're not interacting or locked in with each other. So we want to lock them in at a microscopic level. So to do that, we're going to add this cross-linker. It's essentially a chemical that will react parts of these chains so that they're all going to get locked in each other. And I guess I don't need, let's use this pipette. We really don't need much cross-linker. We're only going to put maybe a drop or two. Let's make it 5 drops.
Just 5 drops.
And that should be enough to get the reaction going. So if I stir it for a little bit longer now, you should notice that the liquid starts getting a lot thicker. And so now if I try to pour it out of the jar, it still has to go a little bit longer. But essentially, you can see it if I just use this spoon, it's starting to gel. Right? So if you've ever played with Orbeez, that's kind of the consistency we want. And so now that this is gelling up, it's considerably harder to pour out, right? It will also, because it's more viscous, it will hold sand much better. And you can see it looks just like this goo. It doesn't flow very much. And the reaction will continue to go and increase the viscosity. Usually, you don't want the viscosity to just increase really quickly. You want this to be a very gradual reaction so that the water at low viscosity has time to get all into those fractures before it becomes a suspension with the sand. But then eventually, we want to release the sand. So let's say that this has gelled up enough, right? It's not really flowing anymore, or it's flowing very slowly. So if we wanted to break the gel, we would have to add a breaker. So what I'm going to add now is I'm going to add a little bit of acid because that helps to start the reaction, like, make it happen faster. And then I'm going to add a breaking agent. And in this case, it's another familiar product. It's just hydrogen peroxide I got at the pharmacy. You can think of it as oxygenated water to treat small wounds, right, to disinfect. So I'm going to use the same thing you use to disinfect, and we're going to use it to break the polymer channels. And so if I like stir for a little bit, you'll see that the big clump starts disintegrating, and it all turns back into a very thin liquid, right? Not very thick. It's easy to pour in or out. Start pouring it back in there. It's not very thick anymore. So the tricky thing is you can mix things really easily, right? You're putting all of this underground and you mix it up. The hard part is to unmix everything. So eventually you'll get a lot of this water flowing back as produced water, and we need to treat it to separate all of the monomer remains, because at the end of the reaction, the polymer breaks down into little monomer units. But the cross-linker actually has, it's like borax detergent. It has boron ions in it. The boron is actually a contaminant, right? You cannot just dump that into the environment. You have to remove the boron from the water and treat it before you can reuse it for agriculture or some other purpose. So then other people in my lab, what they work on is they separate boron out of produced water so that it can be safe to use again. So that's it for this demo.
And this is really how they do it, by the way. In when they're doing fracking, these rheology modifiers, this is exactly the kind of things that they're doing.
Yeah, so this Wargon is very cheap. So because they need so much water to pump underground, they cannot really use a very fancy, expensive polymer because it wouldn't be economical to do. So they have to get creative with things that are cheap, like the Wargon or some derivative of it.
All right, so we have two more quick demos.
That's right.
Which one should we first?
Let's do the sodium polyacrylate. Right, so we have this, I guess we can shift over to the next station. There we go. So we're going to use a lot of water here. And essentially, sodium polyacrylate is another polymer. And you can see just like a white powder. Right now it's dry. But it turns out that it's a polymer that really likes water. And in fact, it can absorb a lot of water like a sponge, but to a much bigger degree than a sponge would. So I have the water here, so I'm just going to add as much as I can until the volume stops increasing, right? And as I add the water, you can think of one consumer product when you find sodium polyacrylate in. You probably encountered it before. In fact, when you were really young, you probably wore a lot of these products. You probably need something to stir it up, sir. I'm just going to use the other side of the spatula here. It seems the polymer is a little bit old, so it's taking a while to absorb the water. Yeah, so maybe it's a little bit hard to see, but these clumps of polymer are absorbing a lot of water. So this polymer is a little old, so it's happening, the absorption process is happening a little bit slowly. But essentially, it's the same polymer you would find inside a diaper, right? So when toddlers are still learning how to go, if there's an accidental release, you don't want a mess everywhere. So they put this polymer, among other things, in a diaper. So it will absorb all of this water, essentially, right? The major component of urine will be water, but anything dissolved in it would also be absorbed in the polymer. And so once it's happening really slowly, but it can actually absorb around 1,000 times its original volume in water. So it will essentially become a big gel, just like what we had with the blue argon. But what happens is if you add some salt, the water really likes to hang out around the salt a lot more than the polymer. So what you would find is that if you had salt water, it wouldn't absorb very much. Or if you started with fresh water and you wait until this absorbs all of the water, and then you add a little bit of salt, the polymer would sink to the bottom and become a powder again. We probably don't have time to show you the whole thing since it's happening much slower than I expected. But if you think back of a diaper, you can really remember how quickly they will increase in volume and suck up all the water. And finally, the last demo we have is a polymer that Matt actually works with a lot. So maybe 80 or 90% of the membranes he's made are made with this material.
It's a wonderful material.
It's called polyethylene oxide, or PEO. But yeah, we're gonna go to the lab here. So I started mixing some of this polymer, which is PO, and you can also see that it's very much like jelly. It's difficult to mix. I put some ethanol in it. That's the solvent I used initially, but we're gonna also add some water. So we have water on this beaker, and I'm just gonna mix it in. Try to make a little bit more. Try to turn this into a gel. So PO can actually, compared to other polymers, it can grow really, really, really long. So this one in particular is 300,000 grams per mole. So a single mole would weigh much more than what we have here, most likely. If you were to stretch out the polymer.
A single mole would be like an extremely large, I don't know, something that weighs 700 pounds, like an elk, maybe, I don't know.
Right. It has tens of thousands of repeat units. So like the single carbon-carbon oxygen that keeps repeating itself, it will repeat itself around 10,000 times before.
Yeah.
Or the chain stops and a new one starts. Unfortunately, because the alcohol evaporated, so it's not really mixing with the water. So this is not gonna quite show you what's happening microscopically, but we also have a macroscopic version of the demo. For that, I don't really need the gloves. Essentially, what happens, a way that you can visualize this polymer chain, you can just think of like a lot of beads that are connected to each other. So I have one of these bead chains that you would find on maybe a fan, a house fan. And if I find the tip, it's a little tangled up. But somewhere in here, we should have to find the end of it.
JC, you're off camera.
This is the part that the less glamorous part. Is it right here?
There you go.
A little bit tangled up. So it's a very long chain, just like a polymer would be, right? So this kind of gives you a sense of how many repeat units one would have. Yeah, thanks, Matt. If it's so long, it's easy to get it tangled up, just like a real polymer. One of the reasons that they have a scrubber is to act very much like a wax once you put some water in it. It is very viscous. And I guess you can keep going. There's the end. So now we have to put it back in, the rest of it. Try to get it in so it doesn't tangle through this way. Oh, the curve of the other. Yeah, it might be too tangled.
Let's just give it a shot.
Essentially, if we go
Yeah, I gotcha. Yeah.
and just start pouring it out. So if this was like the cup and I'm pouring out the polymer solution, right? Just like I mixed it with water and ethanol, what you would see is that it would keep pouring on its own without me having to turn the flask or the heat. Just keep going on its own. This is kind of what happens, right? So it's too tangled. It won't work with this tool.
I think this demo might not quite work, but you can Google self-pouring PEO.
That's right, or you can Google mold effect, find it on YouTube, and some people go crazy and go to like the highest floor of the Empire State Building and throw the chain from there. And so you will see that the chain will arc and travel quite a bit up before it goes down because it's kind of constrained and you cannot turn all the way. So what you would see is that you just give it a little flick and the whole chain will come out of its container, essentially on just from the initial pull, from the momentum it has.
Great. So I think is that open. All right. Okay.
And that's what we have for today.
All right, everyone. Well, we're coming up on an hour, which is kind of what we limited ourselves to. If there's any other questions, we're happy to take them. Also, Trish has my contact information if there's anything you'd like to reach out about or anything else you are curious about.
Are there any questions, guys? You can just unmute yourselves if you want. Everybody's quiet. I'm gonna go ahead and put up my ending graphic, and we can still talk over it if we need to. But we want to say thank you to all of you who came to watch this presentation, and of course to Matt and all of his crew here that helped explain it. Here at Explora, I work for Explora. We do a lot of polymer. We pare it down, of course, for younger people, and we play with different polymers and how to make them and what they can do. So it's really cool to see it in a bigger application and what we can do with that in science. It's very cool. Thank you.
Thank you.
All right.
So let me see. I'm going to go ahead and put this graphic up. And if there's no questions, I just want to thank everybody for coming. I want to let them know if you fill out a feedback form on this event, you could be entered for a daily prize drawing. The link is there. It's a bit.ly. And also today we still have 3 more events coming up. At 1 o'clock, we have measure and report precipitation from home. At 3 o'clock, we have a Facebook Live with our maker team here at Explora that's going to be making musical instruments from home. And then at 4 o'clock, we have a virtual escape room with the supercomputing challenge. So if you guys are interested in any of those, please go to our website and you can pre-register to get your links on our site. And if there are no more questions, I think we'll go. And we hope to see you again soon.
Thank you.
Thank you so much, Trish, for organizing this. Really appreciate it.
Yeah, it was great. Thank you guys so much. Have a good day.
All right. Thank you. You too. Bye.
Bye.
Hi, Trish. My name's Maeve, and I will send you the information about the STEM program.
Oh, that's great. Yeah, I'm the youth intern manager here, and it's always nice to be able to have information.
Yeah, that'd be great. Actually, and I would love to have a chance to talk to you just about outreach in general and that kind of thing. So I'll ask Matt for your email address.
That's perfect. That's perfect. Yeah, I would love that.
Okay.
All right. Thank you so much.